Welcome to This Explainer. Today, we're opening up the ultimate detective's toolkit for uncovering hidden information. In the real world, the data we collect as engineers and scientists is rarely pristine. It's usually messy, it's corrupted, and it's buried deep inside chaotic real-world signals. But hidden within all that noise is the absolute truth. You just need the right magnifying glass to see it.
And that brings us to a really fundamental challenge. Think about it. How do we actually find a hidden signal when it's buried in completely random noise? When you're staring at a jagged, unpredictable waveform on an oscilloscope, or just digging through a massive data array, how do you extract the meaningful stuff from the chaos? Well, to solve this puzzle, we're going to unlock the superpower of the Fast Fourier Transform.
Okay, let's dive right into this. Here is our agenda for today. We'll start by deconstructing the time domain, then explore the power of the FFT, talk about taming spectral leakage, and finally, navigate Matlab's specific FFT tools.
Section 1. Deconstructing the time domain.
When we're dealing with real-world signals, we're usually looking at a voltage changing over time, right? That is our time domain. But Fourier's theorem states a pretty profound truth. Absolutely any waveform in the time domain, no matter how wild or complex, can be represented simply by a weighted sum of sines and cosines. So the frequency domain is really just a different way to look at that exact same signal. It shows us the voltages present at varying frequencies instead of mapping them across time. Let's actually prove this out. It's wild how simple addition creates instant complexity. If we start with a very basic sine wave and then simply add a second sine wave that's 3 times as fast, meaning its frequency is 1/3 of our first signal, we instantly create an entirely new complex shape. The original peaks are completely fundamentally altered.
And, we don't have to stop there. If we layer even more signals into the mix, say adding a third wave that's 1/5 the amplitude and frequency of the original, and we just keep stacking them, the waveform continues to morph. We're essentially building a complex structure using nothing but simple, smooth, oscillating building blocks. And this brilliantly illustrates the ultimate aha moment. If you just keep stacking those precise sine waves until you hit the noise floor, you literally create a perfectly angular square wave. Think about that. An angular square wave is actually just an infinite series of simple, curved sine waves added together. And because we can construct signals this way, it means we can also deconstruct them.
Section 2. The power of the FFT. So that realization completely shifts our narrative from constructing signals to tearing them apart. Now, before the FFT came along, the discrete Fourier transform required operations on the order of n squared. That's a lot of math. But the fast Fourier transform algorithm optimizes this down to n log n operations. This leap in computational efficiency is just a massive, game-changing advantage when you're processing millions of data points. For example, researchers use this exact computational efficiency to analyze massive audio data sets of underwater Pacific blue whale vocalizations, pulling out fundamental frequencies like 17 Hz that are literally barely audible to the human ear. And this kind of computational muscle translates directly into some incredible real-world applications. By isolating specific frequencies out of messy time domain data, we can tune into one specific radio station out of the crowded airwaves. We can isolate bass and treble to remove audio noise. We can even analyze earthquake vibrations to optimize building designs against the most dangerous frequencies, and create more compact file compression just by ignoring the least important frequencies in memory.
Section 3. Taming spectral leakage.
But here is the catch. In the real world, our data is finite. We're almost always analyzing non-integer periods of data, and that introduces a really frustrating distortion called spectral leakage. You see, the FFT mathematics assumes your data has a circular topology, meaning it assumes your time waveform loops seamlessly from the end right back to the beginning. But if your sample doesn't capture a perfect integer number of periods, the endpoints don't match up. This creates an artificial, sharp discontinuity. The FFT actually misinterprets that jagged edge as high-frequency energy that isn't really there, which causes the true energy of your signal to smear or leak right into adjacent frequency bends. And this is exactly why we need a corrective lens. An ideal FFT produces this wonderfully sharp, distinct spike at the exact frequency of the signal. But the smeared FFT, the one ruined by those discontinuous endpoints, gives us wide, blurry peaks. Honestly, it's like trying to read a license plate through a camera that's completely out of focus. We absolutely need a way to fix this blurred, leaked data. Well, that corrective lens is called windowing. Windowing acts like our detective's magnifying glass. By convolving, which is essentially mathematically multiplying, the time domain signal with the shaped window, we pinch the ends of the sample down to zero. This gracefully smooths out those jagged, discontinuous edges, minimizing the disruptive side lobes in the frequency domain and pulling our target frequencies right back into focus.
Now, there are a ton of window types out there, like the flat top if you need strict amplitude accuracy or the Hamming window, but here's the secret. The Hahn window is considered perfectly satisfactory in about 95% of all cases. Because the Hahn window smoothly touches zero at both ends, it entirely eliminates that artificial discontinuity, offering great frequency resolution and heavily reduced leakage. If you don't know the exact nature of your signal beforehand, the Hahn window is hands down the absolute ultimate starting point for your analysis.
Section 4, Navigating Matlab's FFT Tools. Okay, so now that we understand the theory and the corrections required, it's time to look at how to actually code this solution properly. If you're working in Matlab, there is a very distinct difference between the FFT command and the FFshift command. If you just run a standard FFT, the plot is going to output a mirrored reflection in its second half, so the positive frequencies come first, followed by the negative frequencies. It's mathematically accurate to the algorithm, sure, but it is super hard for a human to read. FFT shift, on the other hand, performs a zero-centered circular shift. It takes that raw array and elegantly swaps the halves, placing 0 Hz right in the middle where it is infinitely easier for us to interpret visually. To understand why this extra step is even necessary, you kind of have to look at a historical quirk. As signal processing engineers have pointed out on places like Stack Exchange, in old-school DSP textbooks, arrays often start at an index of 0, which perfectly represents 0 time or 0 frequency. But the creator of Matlab designed all arrays to have an origin of 1. Because of this 1-based indexing, the mathematical output of the DFT gets slightly misaligned from natural human intuition regarding negative and positive frequencies. So FFT shift is that necessary, built-in tool you use to bridge the gap between textbook math and executable code. So the crucial takeaway here is this specific 3-step execution pipeline. First up, you apply your window function, like our trusty 95% Hahn window, to your raw time series to prevent that nasty spectral leakage. Second, you run the FFT command. And a quick pro tip here, you can actually pad your data with zeros to the next power of 2, which forces the algorithm to run significantly faster. Third and finally, you apply FFshift to that output. Do that and you turn a noisy off-center array into a brilliantly clean, zero-centered, and highly readable frequency spectrum. By truly understanding the time domain, utilizing the raw computational power of the FFT, applying windows to correct leakage, and smartly shifting your arrays for readability, you've now got a complete master toolkit. So now that you know exactly how to strip away the chaos and deconstruct the noise, what hidden signals are you going to discover in your own engineering or data science projects? The truth is absolutely in the data. You just have to go find it.